recording. Okay, cool. Alright, so I'm just gonna start sharing my screen then. Okay. Alright, can everyone see my screen? Yeah, awesome. So obviously when we're talking about regularity and non-regularity, there are some definitions that we need to know. So firstly, we need to know cleanest theorem. So cleanest theorem. Does anyone know what cleanest theorem is? If you write it in the chat. Convert regex to epsilon NFA. Yeah, kind of. Yeah, a regex can have a DFA and a DFA can have a regex. Yeah, and that means that the language is regular, as Sid says. So to define cleanest theorem, what we would say is that if a language L is regular, then this language must have a regular, why am I doing that in caps? A regular expression that will recognize this language and a DFA, or a deterministic finite automaton, that will accept or recognize this language. So we have cleanest theorem, which tells us about what happens if we have a regular language, which is, like we've just said, a regex or a regular expression or a DFA. Now, the main thing what we want to know when we do something regarding a DFA, or regarding considering whether a language is regular or not, is to use cleanest theorem. So I'm just going to start off by doing exercise 5. So if I just screenshot that, just so I can start off. And then obviously if anyone has questions, just leave them in the chat. This can be related to this or just related to regularity, non-regularity in general. So essentially, let's just look at the question. So we have exercise 5. Consider the following language over the alphabet A, B, such that we have L, which is the set of words W, where W contains the same number of A's and B's. So essentially, we'll have a language where every word will have the same number of A's and B's. So this can be AB, this can also be AABB, or even BABA. For example, it doesn't matter what it looks like as long as it has the same amount of B's and A's. Now, technically, we can write this in such a way to reduce what we're looking at, because, for example, if we look at AB, I mean, not AB, AABB and BABA, they look different because they have a different pattern. Like, one has a pattern A to the power of N, B to the power of N, but the other has a pattern of B A to the power of N. But because we're only considering the number of A's and B's, we don't need to sort of consider each sort of case separately. So what we can say is, when we're trying to prove that this language is regular, is that we can start off by doing a contradiction. So we'll say, we will prove that L is not regular via contradiction. So we're just going to contradict that L is regular, and hence it must be non-regular. So what we do is we assume that L is regular, and hence by cleanest theorem, the DFA, well, not VDFA, hence by cleanest theorem, because L is regular, or we've assumed that L is regular, then there must exist a DFA that will have a number of states and, well, a finite number of states actually, because obviously we got to remember that a DFA is finite, not infinite. So a finite number of states and will recognize L. So that means that this DFA that we have will, given, let's say we have the set of words, it should accept all the words in that language when we input it into that DFA. So that's that. And the thing is, obviously, like I was talking about before, we have a to the power n and b to the power n, or this form, or we could have many other forms, which I'm sure you can sort of have a look at. But the main thing is that we only care about the number of a's and b's, so we can actually reduce this language down. So what we can actually say is that because we are only looking at the number of a's and b's in the language, we can reduce L to L prime. So instead of making this more complicated and just considering, for example, like this, we're just going to reduce the language such that it has the same output. So we're going to reduce the language to L prime, where L prime is equal to the set of A to the power of n, B to the power of n, such that n is in the natural numbers. Can anyone tell me what this means when we're talking about this? If you just give me like an example in the chat. Yeah, A, B, B, A, B, 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 yep. N number of A's followed by N number of B's. Perfect, yep. Awesome. Nice. So yeah, we have that. So just to clarify, like I said, we're looking at the same number of A's and B's. So even though we have this, we know that L prime is a subset of L. So although we can have like these two strings that have the same number of A's and B's, and this is in L prime, but this isn't in L prime, because we're only looking at the same number of A's and B's, we will get the same output for each DFA. So we just state that here. So we'll say that L prime given, well, L prime will have the same output as L. Now, you don't need to specify this. We know this because L prime is a subset of L. So we don't need to say or specify this explicitly. It's implicit. So I'll just put that in like brackets here. Okay. I'll just write when put into the DFA. Right. And then now we have this language, because it's a subset of L, if we show that L prime is non-regular, and because L prime is non-regular, L must be regular, because we can't have a language that has non-regular parts in it, right? So what we're going to do is, instead of proving that L is not regular, we're going to prove that L prime is not regular. So what we're going to start to do is we're going to do that. So let's say we have this DFA, obviously, we've assumed that L is regular. This DFA will have some form in which it will accept AN, BN, right? And this will kind of look something like this. So if I copy paste this over, can everyone see that? Or shall I like increase it a bit? Hard to see. What about now? Is that good now? Yeah, awesome. So let's say we have the state xm. So we're just theorizing here. It looks like I took my glasses off. I'm sorry. Let me see if I can make it any better. Hold up. Okay, that looks better. Cool. All right. So for example, let's say we have the state xn such that we have inputted. So we've inputted this a to the power of n. Now, one thing I'm just going to be clear about, just so that you don't lose marks, is that when you're doing, for example, xn, it's not equal to xn, where x is a capital letter. Because I was actually talking to Todd the other day, and we were talking about this. So just make sure when you're doing your answers, when you're doing your proofs, just make sure that everything is all the same. Because, for example, if you have wrote this, these are actually two different states, even though it's quite similar. So yeah, just to keep that in mind. So going back to this, and so we have the state xn such that we have inputted a to the power of n. Now, we also have state xm such that we have inputted a to the power of m. Now, for these two parts, we're just theorizing here because obviously when we look at the same number of a's and b's in a string, for example, when we're looking at L prime, there must be like A, B, 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 right? So what's m? M is just a number. I'll define that in a moment. So actually, I'll do it now, just to make things easier for you. So let's say we have x and we have inputted an, and we have a to the power of m, right? In the original lecture, Todd said not to draw this, though. He said it was too general. Yeah, so you don't need to draw it in your answer. You don't actually need to draw it in your answer. I'm just doing it to sort of visualize it. The main point is that when you just draw this and you just don't really say anything, then it's like, if you're not explicit about what you're talking about and you try to just use the drawing to show something, it's not going to show what you mean, and hence you won't be able to sort of see, when you look at your own proof, you won't be able to see how the states are inequivalent, for example. So, like I said, we have the state xm such as we have inputted a to the power of m, and let's say that, so if I just define m before, so let us say that n and m are in the natural numbers such that n is not equal to m, right? Now, if n is not m, obviously we can have n is equal to 1 and m is equal to 2, for example. So what do you think the state xn will will accept? So if we have the state xn, what is it going to accept once we've reached that a to the power of n number of a's? B to n. Perfect. And then what about xm? What will it accept? B to the power of m. Yep, perfect. And so if we know that n is not equal to m, that means that these states, xm and xn, will have different states. So they're not equivalent states. So we can say this explicitly by saying that...
Yeah, please.
Sorry, what? Okay, I'm going to continue. So let's say we have that, and then we can say that for xn, it will accept b to the power of n, but it will reject b to the power of m, because obviously we need n b's when we accept n a's, or m b's when we accept m a's. Now, because we know how to show that the states are equivalent. We just need to show that these states have a string that is accepted and a string that is rejected. And we also need to show that for both. So we can say whereas for xm, we accept b to the power of m, but reject b to the power of n. Now, because obviously we've just shown that, it means that these two states over here are not the same, they're inequivalent. And because we know there are countably infinite amount of states, so just to clarify, because we know that there are n number of states, because we're looking at n number of a to the power of n, b to the power of n, so there'll be n of these strings. Because there's no bound on n, and that n is in the natural numbers, we know that the natural numbers are countably infinite, right? So because the natural numbers are countably infinite, we know that hence we can say that xm and xn are inequivalent. So when xm and xn are inequivalent, since they are both in the natural numbers, how do you turn off joining / leaving noises? Honestly, I have no clue. Might be a question for someone else. But hence, xm and xn are inequivalent since they are both in the natural numbers. Well, and since they are both in the natural numbers, then we can say that since we are both in the natural numbers, we can say that there exists countably many, or we can say infinitely many states xm and xn such that they are inequivalent. So what this means is that when we have this state over here, xm and xn, because they're inequivalent, we can't reduce that DFA any further. So for example, if I take, for example, the DFA for A star, technically it would just look like this. So if I just draw that, we can move up to the stage if you guys want. It's up to you guys if you want to vote, just like if you vote. But yeah, continuing on. When we look at this DFA for A star, obviously we can have 1 and 2 and all the other states are accepting. But if we look at the minimized version of that, it will just be a state pointing to itself, like that. So essentially, that's what we get when we minimize it. But because all the states are inequivalent for xm and xn, because there are an infinite amount of inequivalent states, we can't minimize this any further. And hence these states will always be infinite because this is the minimal DFA that we have. And hence because of that, we know that obviously a DFA is finite, right? So yeah, we're just proving that a language is irregular. The language that we're proving is irregular is this one over here. So that's L is equal to W, where L is equal to the set of words W, such that W contains the same number of A's and B's. Cool. Bro. Yeah, English. But yeah, so like I said, we can say that there exists infinitely amount of states xm and xn such that they are inequivalent, And because we can't minimize this DFA any further, because they are inequivalent, that means that there are an infinite amount of states. Now, having an infinite amount of states contradicts the finite property of a DFA. So obviously that means that the DFA isn't finite. So that can't exist. So hence this DFA recognizing L prime, because obviously we're talking about L prime here, which I defined further up. So I'll just scroll up a little bit. Hence this DFA recognizing L does not exist. And hence, because we have no DFA, just to double check, this only works on the rejecting states because you can't minimize them, right? Versus the accepting states where you can minimize with the DFA. So it's not just the rejecting states, it's also the accepting states that you can minimize. So like I was talking about here, the A star DFA has an infinite amount of accepting states, but we can just reduce it down to that. But because we have this over here, we have these ones over here, because there's like two states. You can't sort of minimize that for any n, because there's no sort of memory tracking in a DFA or anything like that. We just look at one character at a time. And so because we're looking at one character at a time, we can't sort of have the property of minimizing that, if that makes sense. Just let me know. But yeah. So hence this DFA recognizing L prime does not exist. And hence, because it does not exist, because we do not have this DFA, by contradiction of the finite property, L prime must not be regular. And since L prime is a subset of L, then L must not be regular as well. Hence, by contradiction, is it possible for you to highlight the main points we need to make for this? Yeah, sure. I can zoom in a little bit as well. Hold up. Is that a bit better or a bit more? Is that okay? That's fine, cool. Awesome. And then hence by contradiction, also, I need to like stop with my capitals. Oh my god, I can't do English. Hence by contradiction, L is not regular. Okay, so yeah, that's the sort of idea that you're trying to look at. Main idea, which I'll just go through now, is firstly, we assume the language is regular. Now, I'll also talk about how we can do this for both regular and non-regular languages, because obviously, when we have a regular, when we have a question that's asking if it's regular or not, you might get a bit confused because you will have to test like sort of different edge cases. So you can actually use this as well for looking at if a language is regular or not. So we assume that the language is regular, first of all. Hence, by Cleaner's theorem, it must have a DFA. And then we start to describe the DFA. And we need to show that this DFA cannot exist or can exist. So when we describe this DFA, we can talk about the states reached on input. If it is regular, you should be able to draw it. You should be able to draw the DFA. Because I'm not sure, I don't think they'll ask something that's really, really complex. So you should be able to draw out the DFA once you've described it. And since the DFA exists and it recognizes the language, then the language is regular. and that would be due to cleaners theorem. However, if it isn't regular, you need to prove there are a infinitely or countably many, well, you need to prove that there are countably many or infinitely many states that are inequivalent, hence no longer can be minimized. So these can't be minimized. So countably many and infinitely many are the same. Yeah. So there's no difference between them. It's just that there's different ways you can say it. I just tend to say either countably many or / infinitely many, just so they know what I'm on about. Because countably many does mean infinite, but I just want to be clear with my answer, hence why I write that. So yeah, there are many states that are inequivalent, and you cannot minimize this DFA anymore. Hence, the DFA is not finite, which is a contradiction. And so because of this contradiction, we know that if I can type, this language is not regular. What do I mean by step 4? So it just means to describe the DFA. So we're going to be talking about the states that we reach with regards to a specific input. For example, for a to the power of n, b to the power n, we can consider xm and xn as the states, like Danny has just said, for example. So yeah, essentially it just depends on what we're looking at in terms of if we've inputted a certain amount of A's or B's or whatever you want to look at depending on the question. And yeah, show that for all mn that they are inequivalent. So yeah, hopefully that does make sense. If I am waffling, just like let me know. But yeah, that's the sort of idea. Can you go over briefly what you did after showing the picture of a DFA? I'm still confused on what specifically made it not regular on L. So L prime, when we look at L prime, obviously L prime being this, so a to the power of n, b to the power n, because when we have a to the power of n, we can't accept b to the power m, right? Where m is not equal to n, because that's not in the language. So because it's not in the language, we'll have many different states that will have a to the power of n for all n. And hence there will be an infinite amount of states. So this is essentially what I mean. Because there exists one state, a to the power of n, that accepts a to the power of n for all n, and b to the power of n as well, because obviously if it was just a to the power of n, then it'd just be like a star, but we also have that b to the power of n, which is a bit different. By the way, if you are confused by this is not for this specific approach. I'm just showing you a DFA that you can sort of utilize and just draw to sort of visualize it. Hopefully that does make sense. Obviously make sure to ask your questions in the chat. So yeah, so we're looking into a subset of L that isn't regular to prove that since there is a set that isn't regular, concluding that the whole set of L should not be regular. Basically, the only reason why we're doing this is because we would have to show that this is also non-regular as well, because if we have like many different forms of a language, which is a bit harder to do, we can just reduce it down to a specific language. Because if you have a language that can only be represented, if we have a language that is a subset of another language, so let's say L1 is a subset of L2, where L1 is non-regular, you can't have L2 being regular. So because n is a natural number, there's infinitely many states, so it's not a DFA, i.e. not regular. Yep, perfect, that's it. Because you can't have infinitely many states in a DFA. A DFA is finite for a reason, hence it's non-regular. Yeah. So yeah, that's basically it in terms of sort of proving that exercise 5 isn't regular. Yeah, I'll scroll down. What I'll do is I'll put a screenshot in the chat. Very wordy, but I think I get it, thanks. Yeah, the thing is with these ones, you're gonna have to write at least a paragraph. I was talking with Todd the other day, so I could like sort of get my head around this. You are gonna have to be very explicit with what you're talking about. You can't just make it really implicit, because of the nature of the question. So yeah, I'll put this in the chat. And yeah. And one thing I will also mention as well is that for this question that I did, you don't need to always sort of reduce a language down. You can also say, let's say for example, if you look at this question, which is quite similar to the one that we've just done, but it's just that we have more A's than B's. Obviously, this language, we can prove that it is non-regular without having to reduce it, because we know what the language is in a notation form. Whereas here, it's not in notation form, and hence it might be easier for you to reduce the language down to some other language that is a subset as well. So yeah, I think you should have a go at exercise 6 and 7. I just don't want to go on too much longer, because I feel like there'll be too much time that I would just be wasting by yapping. But you know, is there a specific rule or fact that allows us to just actually prove a regularity just using a subset of the original set? No. So you can't prove the regularity just using a subset, because, for example, I could have a subset that is regular, but then another subset that isn't regular in a language. So you can't prove regularity, you can only prove non-regularity, if that makes sense. So if a subset isn't regular, So if a subset isn't regular, the set it's a subset of isn't regular. Yeah, that's it. God, okay. Yeah, it's pretty hard to get your head around, because it's like, how would I visualize it? L prime, because it's like this. If we have like property 1, P of X and Q of X, right? If I talk about it in terms of MLFCS, if we have this property X, Q of X, and then R of X, where P of X is in R and then Q is in R, Q is in R. If P of X is regular, and then if Q of X is non-regular, this can take finite states to recognize the language. Whereas we have, for a non-regular language, it will take infinite states to recognize the language. And so we can't have R that it's finite. So we can't have something that's finite, because if we have R that's infinite, because we have R, let's say R has a DFA, but the subset of R is infinite, that wouldn't really make sense because if we have R that is infinite, then Q must be infinite. Because Q is a subset of R. So yeah. How do you decide if a language is regular or not when a question asks you that? Yeah. If it's as Shay says, so if it's a DFA, I mean if it's regular, you can try to represent it as a DFA. If you can't, it's not regular. Like I say, I'll put this. What I'll do is I'll put this screenshot in the recap. Regularity slash non-regularity proof. Okay. Yeah, usually you can tell when they ask you for each specific amount of character, but don't rely on that. Yeah. But yeah. That's basically it on my part, I think. Is there any other questions? No worries. Awesome.
Lovely.
Lovely. If it asks to show what a language is regular, okay. Awesome. Okay. Shay, I'll hand it to you then.
Cool. Cheers for that. Yeah, Pokey, what I might do is like, or what I'd do probably is draw out a DFA and then say by Clean's theorem, because we can represent it as a DFA. This is a regular expression, and a regular expression represents regular language. Maybe just write a sentence or two explaining why the fact that you have a DFA makes it regular. Okay. Do you guys want to take a break, or shall we carry on with minimal automata? Carry on. Okay, we've got to carry on. Let's move to the stage though, because I think the sounds. Yeah. Cool. See you there.